So I put a number of new things on the class website, in particular, a new version of the SW thing, also, which is the whole set of notes. A new version of the effective field theories. And then I added something that I'm going to be talking about today, 2 or 3 things from Weinberg's book. Although I have to say there are a few typos, and I'll try to remember to mention what the typos are. So the thing I'm going to talk about, which is explained in the PDFs that I took from Weinberg and put on the class website today, is another example of Dirac brackets. So the original Dirac brackets, of course, were introducing this notation, and the new thing by Dirac was introducing this quantity, which hadn't been a notational device before that. The new Dirac brackets are a way of dealing with theories that have constraints. And so let me start by reminding you what a Poisson bracket is. Incidentally, the Poisson bracket also goes back to Dirac. Of course, the Poisson bracket is an invention of the 19th century, maybe even the 18th century. But Dirac noticed that you could interpret the rules for quantum mechanical quantization by saying that the commutator of 2 quantum variables was I h bar times the Poisson bracket of the same 2 quantities. In fact, the story that I read somewhere is that Dirac often went on long walks. By the way, so did Heisenberg. Walking is probably the best exercise. In particular, you tend not to fall the way I did. I tripped on, I told you guys this on Monday. So anyway, Dirac, on one of his walks, thought there was something to do with Poisson brackets, that it was somehow related to the quantization of quantization rules of quantum mechanics. But he couldn't remember what a Poisson bracket was. And when he got back to Cambridge, and when the library was open, it's probably always open. Anyway, when he finally got to the library, he was able to look up what a Poisson bracket was. And he said, well, the quantization is the commutator of 2 operators is I h bar times the Poisson bracket of 2 operators. And but what he realized later was that that there was a problem in this rule in the case of theories with constraints. And one of the things that is a problem in the way we teach physics is that we always teach the simplest thing first, and that goes into people's minds as being the archetype of reality, and then it turns out that sometimes turns out that it's not true, and we somehow don't change our pedagogy. And so For example, the standard model of particle physics is a gauge theory, and in fact it's a gauge theory in which there's a scalar field that carries charge in the sense that at least two components contain electric charge, two other components are electrically neutral but carry hypercharge. The other fields are fermions, which have constraints and aren't simple scalar fields. And then the other fields are the gauge fields, which, as we'll see today, or as you already know, have constraints. And then, of course, there's gravity, which also has constraints. So, in other words, the real theories are loaded with constraints, and we've been thinking in terms of, and teaching students in terms of theories that have no constraints at all. In fact, I'm guilty of this also, because anytime I try to do an example, I pick a single neutral scale field, which of course is so much easier to think about, but which doesn't have constraints. So let me remind you what a Poisson bracket is, and in fact I want to use, there's always a little bit of ambiguity in notation, and so as I said, I put a number of things on the class webpage, and these things taken from Weinberg are some. So this is the definition of a Poisson bracket, and if we're dealing with simply quantum mechanics, then it's partial A, partial psi A, partial B, partial pi A, minus partial B, partial psi A, partial A, partial pi A. So here the pi's are canonically conjugate to the a's, so pi A is the partial of the action density with respect to psi A dot. And in the case of a simple scalar field, one can take these equations that define the momenta that are canonically conjugate to the velocities, and one can invert those equations. In fact, in the case of the cases that we're always considering in textbooks, those inversions are immediate, and one can construct the Hamiltonian and so forth. Two sorts of problems can arise. One is that you just can't find, you can't relate, there are no relations whatsoever that express all of the velocities in terms of the momenta and the coordinates. Actions for which that's true are called irregular. And I have to check how you spell irregular. But anyway, you can imagine there's one R or two in irregular. Actually, David Amdahl and I were considering another case recently, namely, what if the action is regular, but it's hard to find the velocities in terms of the coordinates and momenta. And we call these actions awkward and very awkward. And the difference between awkward and very awkward is, in the awkward case, you can find a Hamiltonian. In the very awkward case, only God can find a Hamiltonian. Since there isn't any God, you don't know what's going on. Okay, now, so when Dirac first invented his new Dirac brackets, which I haven't yet defined, he was considering the case of quantum mechanics, but of course he generalized it to quantum field theory, and that's the case I'm going to be discussing. And in the case of the generalization for Poisson brackets, what you have then is that AB Poisson is an integral dqz. And of course, we're summing over A, and Weinberg thinks of this as an index, let us say alpha, and then space. Not time, because just as commutators are taken to be equal time commutators, in other words, we're not trying to do commutators at unequal times, we're only considering equal time commutators, so too Poisson brackets are always defined for equal times. So this index alpha, this index A specifies a space variable, a location in three-dimensional space, and then an index, say, alpha, that tells you which field we're talking about. Well, I think Weinberg uses probably an I. So in any event, this thing is partial of, in fact, let's do this a little more carefully. Let's call this A of AI of X, B J of Y Poisson, and I'm a little worried that I'm going to get into a space-time issue here. But anyway, it's partial AI of X, partial psi A, let us say, I of Z, sorry. And then partial B, and here we're talking Y, and I said there was a J there. So this is then partial pi A of Z, and then minus the same thing with A and B interchanged. And so this is partial, let us say, Bj Y, partial psi I A of Z, partial A I of X, partial pi A of Z. Okay, so that's the Poisson bracket in the case of field theory. And
wait, Kevin, are A and B, have they been quantized yet? Are they quantum?
No, we're at the classical.
They're just classical variables.
And well, let's see, I've got, where's the nice list?
Yeah, I think maybe, yeah.
All right, so I skipped this equation.
Why don't we index the pi with I? Or
Give me that again, what?
Why don't we index pi with J? Why isn't this how psi?
Oh,
has
yeah. All right, it would. Well, if I'm doing I, J, it would have to be K.
Yeah.
So let us call this K. The thing is, all right, let's, you see this other, one index is a space index, Z. But the other index is, labels the field, and it can be a space-time index. So this could be, if there's just one field, this could be the zero component, well, not one field, but one vector field, say. This could be zero or space. This could be a time index or a space index. But it could also be an index saying what field. And so let me stay with Weinberg's notation here. Just A, and I've already departed a little bit from mine,
And these are
because
just
I've made
in
the
the-
space part explicit.
These are just, in the regular sense, just dual space variables, right?
I'm
It's
sorry,
just-
say it again?
These are just dual space, they're conjugate, they're canonically conjugate variables. right?
Which?
The psi and pi. They're not.
Well, we'd like them to be. Let's put it this way, in the theory, without constraints, they'd be canonically conjugate. Modulo a sign, maybe. Now, one thing that is let's see, we're still talking about the Poisson bracket. You can see that the Poisson bracket is obviously anti-symmetric. It's also true, and it's easiest if instead of going to this more elaborate notation, we just look at this and imagine summing over A, where A is space as well as a mu index and maybe a which field index. It's not hard to show that, for example, A, B, C Poisson would be then partial A, partial psi A, partial BC, partial pi A, minus partial BC, partial psi A, partial A, partial pi A. And if you then realize that, of course, the derivative of product is the derivative of the first times the second plus the derivative of the second times the first, then what you find out is that this is equal to B times AC Poisson plus C times AB Poisson. So the Poisson bracket has that rule. It also satisfies the very nice Jacobi identity, namely that if you have a Poisson bracket with a Poisson bracket, so this is the PP identity, B, C, A, P, P plus C, A, B, P, P, 0. So you can work that out, and so the Poisson bracket has all these nice properties. So the problem is that one has constraints, and let me just give the very simplest example of such a theory with constraints, field theory with constraints, is the one Weinberg considers he considers it in detail in his section 7.5, and then an abbreviated version of it is in 7.6. And so what you have is a Faraday tensor there, minus a half m squared v mu. So this is a massive vector field interacting with some current J mu. And here the Faraday tensor, as usual, up to a sign, is d mu v nu minus d nu v mu. And by the way, the colloquium this week should be worth going to. It's on coherent neutrino scattering, and I remember actually when I was a graduate student, Schwinger gave a lecture on coherent scattering, and it was really quite magical.
It's
And
a woman coming
What?
from Duke. Is that, I read the email earlier? It's a woman from Duke. Is that what it said?
yeah, she's from Duke.
Well, you had I think an index in the Lagrangian, the v mu on the second term. Is that
V mu
They're both mu.
Yeah, yeah.
Okay.
It's a Lorentz scale product. Sorry about not having any candy, I just didn't get to Costco yet.
No.
So probably, so I'm gonna hold classes next week, there's no exam, but classes in the usual place at the usual time, and if for some reason the room is taken, we can go to another room. There are about 4 rooms, and worst comes to worst, we go to my office. Oh, I don't know, it might not be room there. All right, so this looks innocent enough, but in fact, if you compute the pi mu, well, this is partial the action density with respect to d0 a mu, or equivalently partial L partial a mu dot. What you get here is minus f0 mu. And that's fine at first. If mu is I, then this makes perfect sense. It's the analog of the electric field in the ith direction. But what you see is that pi 0 is actually 0, because f0, 0, f being anti-symmetric, f0, 0 just vanishes. And this is said to be a primary constraint. And then, if you go further and look at what the 4 Lagrange equations are, then you find that one of them is dI pi I is equal to m squared v0, and Weinberg wrote plus j0, I guess that's right, all right, plus j0. There's a typo somewhere and it concerns plus and minus there, but I think this one is right. Any rate, this is the version, this is like Gauss's law. It's the constraint that arises from, well, it's a constraint because these are momenta. This is a field, and then this is some, whatever it is, an external current or something involving the pi's and pi's. And normally an equation of motion has some second-order time derivatives. That's how the normal equations of motion go. It's something double dot is equal to something else. Here, it's just, there's just a single dot here, namely that pi I is an f0I, and f0I has a time derivative of vi. So this has a vi dot in it, but there are no double dots. And this is called a secondary constraint. The difference between primary and secondary is not important, and in fact, when one deals with Dirac brackets, one doesn't need really to distinguish.
So where did the secondary constraint come from? What did you do? Did you use
It's just the Lagrange equations, which are...
Oh, okay, you just
in other words,
yeah.
d mu of partial L, partial... Oh, hey, I switched to a mu. This was, of course, completely stupid. It's v mu.
Yeah.
So this is v mu.
Oh, yeah, that's...
So this is Now I've got to get the right sign here. What are we talking about? It's
Mhm.
it looks like this.
Mhm.
All right, so I hope I got
Mhm.
Lagrange's equation right. But, tell me if it's wrong. Let me write it a little more. Okay, so in other words, Lagrange's equation for V0 gives you this.
Yeah.
And so the question is what to do about constraints, and what Dirac said, and I must say I find this pretty amazing that he invented this. It's really, he was an absolutely remarkable man. So N and M are labeling the constraints, and these constraints we're going to call chi sub n. This is Weinberg's notation. I don't think it's the greatest notation, but anyway, this is what he has, and so I'm following it. So Dirac invented then the idea of taking the Poisson bracket of the constraints and defining a metric, and not a metric, a matrix. And this is obviously minus CMN. And that's just simply because the Poisson bracket is anti-symmetric. And now there's a feature of anti-symmetric matrices that's interesting, and it's that an anti-symmetric matrix, to have a non-zero determinant, it has to be of even dimension. If it's of odd dimension, it turns out that it's a zero.
Wait, so Kevin, I have a question.
Yeah.
Yeah, so whenever you say, do you take the Poisson bracket of the constraints? Like the constraint is an equation. And so, do I just take the Poisson brackets of left and right sides? Or? Okay.
Brilliant question.
Yeah.
Okay, so let's look at these constraints. And we're looking at them in the context of a massive vector field, which is a simple example. So the first constraint at space point x is just pi 0 of x at some time, but make it times 0. Pi 2 of x is, and in fact, let me use the index k here. Okay, so in other words, the first case was pi 0 equal to 0, so the constraint is chi n equals 0. The other one is this equals 0. The thing that's 0 is if you subtract the right-hand side, then you get 0. And here, let me compute this Poisson bracket for you. So let's compute C1x comma 2y which is the Poisson bracket of chi 1x with chi 2y. And so this is the Poisson bracket of pi 0 of x with dk pi k of y minus m squared v0 of y minus j0 of y. So it's this Poisson bracket. And now what will it be? Well, the general rule is you integrate over space and you sum over the space-time indices and any other indices, and you form this structure here that's the Poisson bracket expression. And so this is an integral d cubed z, and well, you can see the first term is going to be 0, because the first term would be like this: partial pi 0 of x, partial v mu of z, and then I don't know why I had a bracket. Well, this bracket is not a Poisson bracket. This is just an ordinary bracket. And then it would be other stuff, but this is identically 0. But then the next term, the other term is partial, and now the second one, this, which is del dot pi of y minus m squared v0 of y minus j0 of y. Partial of all of that with respect to v mu of z. And then that's multiplied by partial pi 0. Whoops, it's lowercase 0. Subscript 0. Of x partial pi mu of z. So the first term is 0. And now you see this one works if mu is 0. And if mu is 0, it works over here. So we get a non-zero contribution. And what else do we have? We have two minus signs. That gives us a plus sign. We have an m squared. And so let me skip up to here to use this blackboard. So this is integral d cubed z. And I'll cancel the minus sign, so it's m squared partial v0 of y partial v mu of z is delta mu 0 delta of z minus y. And over here it's also delta mu 0, and it's delta z minus x. And so all of that, when you integrate over z, gives you m squared delta of, and you sum over mu, this is delta of x minus y. So what we have here then is that the Poisson bracket of, let us say, chi 1 x, chi 2 y, which is C1x 2y Poisson, is m squared delta of x minus y. This is all unfamiliar, and to most of us. And in fact, I think it's unfamiliar to a large fraction of the physics community. Dirac published it in, he wrote a little book on quantum mechanics. And in the little book on quantum, and when I say little book, I mean it was this big, and it's about as thick as my thumb, or maybe my index finger. And part of the reason why it was short is that Dirac never used extra words if he didn't need to. And by the way, another story about Dirac is that he was once sitting in a room, maybe it was a dentist's office or a doctor's office or something, and he was sitting there and there was a woman sitting there knitting, and he watched the woman knit, and he invented, she noticed that he was knitting, and she explained, he explained to her maybe that he realized how she was doing that, but he then said to her, you know, you can do it a different way. And so he had invented another way of knitting by watching the woman knit. That was Dirac, and there aren't many Diracs in this world. Now, if you have an anti-symmetric matrix, the inverse of the anti-symmetric matrix, well, at least in this case, is minus the metric. Or there's a minus sign here. And in fact, in this case, C inverse, and Dirac, Weinberg writes it as 1x 2y, is minus m squared delta of x minus y. The minus sign comes from the fact that C is anti-symmetric, so its inverse has to be anti-symmetric also. I guess it's that if you have the product of two anti-symmetric matrices, you can get a symmetric matrix. But if you have a product of an anti-symmetric matrix times a symmetric matrix, it'd be hard to get a symmetric matrix. I don't know if that's a theorem, but in any event, it turns out that that's how the inverse goes. All right, so let me see, what do we have? So far I've just defined Dirac's matrix C, which is the Poisson bracket of constraints. Skip that. So here's the remarkable thing. What Dirac said was that the quantum commutator should be something that people subsequently have called the Dirac commutator, the Dirac bracket. And this Dirac, well, I times the Dirac bracket, and here we've got h bar equal to 1. And the Dirac bracket is the Poisson bracket minus a Poisson bracket with one constraint, the inverse of the matrix of Poisson brackets of constraints and then the other constraint, B Poisson bracket, and of course you're summing over all constraints here. So it's a repeated index, and this index n is a space index among other things, and so you're integrating over space once here and once there, and you're summing over discrete indices twice. Okay, so that's Dirac's prescription, and as I said, you have to be able to sit in the room, watch a woman knit, and invent a new stitch to be able to invent this. In any event, what Dirac pointed out, among other things, was that the Dirac bracket is anti-symmetric. And, well, that's kind of obvious because it's defined in terms of that that's anti-symmetric, and then, well, this is kind of tricky, actually, because if you interchange A and B here, it's like interchanging M and N, and then you have an anti-symmetry here. C inverse is anti-symmetric. So that's where that comes from. But it's also true that ABC Dirac is AB Dirac times C plus B times AC Dirac. And then there's a direct version of the Jacobi or Jacobi identity. Okay, or equals 0. So, the Dirac bracket has all these nice properties, and it also turns out that all the constraints have vanishing Dirac brackets with the operators of the, or the variables of the theory. All right, so we've computed one of these Dirac brackets here, namely that, not Dirac brackets, but the Dirac matrix that's anti-symmetric is m squared delta of x minus y. The inverse metric is, did I write it down? Yeah, it's minus m squared. Oh, sorry, it's m to the minus 2. Somebody should have called me on that. It's m to the minus 2 delta of x minus y. And it's kind of evident that if you have the Dirac bracket of pi 0, or let us say that if we have chi1 with chi1, we're going to get 0. Chi2 with chi2, we're going to get 0. Those Poisson brackets vanish. Okay, so let's now.
Wait, I one more
Yeah.
question. So your index on this constraint matrix has a continuous variable in it. So whenever we think of doing matrix multiplication, do we also need to integrate over some common variable? Okay, cool. So really there's like an integral hidden in this equation for the Dirac bracket. Or I guess two integrals.
Yeah, right.
Yeah.
Like right here, you've got two integrations over space and sums over other things.
Sure.
And let me grab more chalk here now.
Question, Kevin. Way back over here, your A, B, and C over here, are those all abelian operations, or are they just functions?
I'm thinking in terms of, well, when you're doing a Poisson bracket, you're thinking of things being classical.
Okay, that's the only the reason I was saying is the difference in where the C
No,
is.
I completely agree. Yeah, absolutely.
Yeah,
So,
we can't go, the Poisson bracket is inherently classical thing. There are not operators in the case of just the regular Poisson bracket. That's-
Well, since I hadn't seen all of this before, I thought maybe this was something new.
yeah.
Yeah, you know, that's what, like, I've never seen that definition of, like, to
Which
construct
field?
the Poisson
Which, Poisson bracket or the?
Well, I guess just for the classical field, the Poisson bracket is the classical field you're at.
Okay, so let's do another example here. Now, okay, those were the constraints. don't want to do too many things that are trivial here. All right, let's figure out what the Dirac brackets of some of these things are then. And let's start with the easiest one. So let's do Vi of X, Vj of Y, Dirac. Now, first of all, this is going to be Vix, Vjy, Poisson, and that's clearly zero, because you need to be able to differentiate with respect to both, get non-zero results when you differentiate, one with respect to v's and the other one with respect to pi's. But the next term is going to be an integral d cubed z, and now it would be first of all a Poisson bracket of Vi of X with pi 1 of z, say, so that's pi 0 z Poisson, and then that's multiplied by the inverse metric here, the inverse matrix here, and so that's a minus m to the minus 2 delta of
should there be an additional minus sign due to the definition of the Dirac bracket, which would cancel with the minus sign that you have there? Is that the case?
where do you want?
There's a minus
sign here. Yeah, minus m squared.
Oh yeah, and there's another minus sign in the definition of the Dirac bracket, right?
The bottom.
In the very bottom equation that you've written down.
All right, hold on. You're right, there's another minus sign, this minus sign. And so we need that there. Thank you. And here we have let's see, if that's z, this is z minus I guess it's z minus y. And then we would have here, wait, no, I think this is wrong, hold on. This one is dk pi k of z minus m squared v0 of z minus j0 of z, comma, e j of y Poisson Okay, I think that is Z minus Y. So what bothers me here is we only have one, I'm just doing one integration, and I thought we should be doing two integrations. In any event, this thing is going to be 0. The other term is here, bj of x pi 0 of z plus on, and then so on and so forth. Well, both of these are 0. And so this one is just identically 0. So what we get is bi of x, bj of y, Dirac, identically 0. That one is clearly 0. Now now we want to compute a couple of Poisson brackets in order to compute the Dirac bracket of bi with b0, which will be non-zero. And, well, we've got a lot of workspace, so let's do it over here. So let's first do bi of x, b0 of y, oh, I'm sorry, pi 0. In fact, I'm doing pi 0 of z because I'm going to use it in an integral or a Dirac bracket. So let's do that Poisson bracket. So this Poisson bracket is going to be a d cubed w of partial b0 of y, partial b mu of w, partial pi 0 of z, partial pi mu of w, minus partial b mu w, partial pi mu w, and up here, partial pi 0 of z, partial b0 y. And now what we can see is that this gives us, this works for mu equals 0. Both of them are going to give us delta functions. This term is going to be 0. And so this is going to be d cubed w. They're going to be 2 delta, Kronecker deltas, 0 mu squared, say, and then delta y minus w, delta z minus w, and this all gives us, oh wait, where did the I go? All right,
Well, I
this
think
was supposed to be a 0, and I left it out. And so when we sum over mu, we just get one value, and so this is just delta of x minus z, but where did y get into this act? This is supposed to be an x. And this is supposed to be an x. And so this first thing is delta x minus w, z minus w is delta x minus z. So this is that Poisson bracket. Another Poisson bracket that we're going to need is dk pi k of z with bi of x Poisson. And so this is an integral d cubed w of partial of dk pi k of z with respect to v mu w, pi mu w, partial vi of x, and then minus partial v mu w partial phi mu w. Unfortunately, what I'm writing on the board is not on the class website. What's on the class website is just what Dirac, what Weinberg wrote about what Dirac wrote. And so these other terms are partial vi of x, partial k pi k of z. And so what's this? Well, the first term is going to be 0. The second term is going to give us a delta I mu a minus sign, a delta of x minus w, and then this part is going to be a delta mu k, and that's going to be a dk of a delta of z minus w. And so this is going to give us a minus di of delta of x minus z after one is finished cooking. Okay. Is that all right, or do you want to see more? Do you want me to evaluate that more carefully or not? All right. So now we're going to try to get the Dirac bracket of VI with V0. And of course the first term is the Poisson bracket, and that just vanishes because wait a minute, why does it? Oh. Now I'm really puzzled with my, oh yes, okay, those are Poisson brackets, okay. All right, so here's what we want to compute. We're trying to compute the Dirac bracket of Vi of x with V0 of y, Dirac. Well, the first thing would be the Poisson bracket. But this is identically 0 because you have to be able to differentiate with respect to a coordinate and a momentum, and these are both coordinates. The next term is if we look at this over here, it's minus the Poisson bracket of the first with a constraint, the inverse of the constraint matrix, second constraint, and then second object, and then that Poisson bracket. And so I made that out to be the following: plus I m to the minus 2 integral d cubed z of vi of x pi 0 of z Poisson times dk pi k of z minus m squared v0 of z minus j0 of z, comma, v0y Poisson. And Ordinarily, this would be another variable w, but there was a delta of z minus w in the C and C in the C inverse. Oh, and hold it. So what we need now is minus. So we've got to. Got this thing written twice and I don't. Oh, right. That's right, we have to sum over all the constraints. So the ones I computed were V0, pi 0, and this thing with VI. Well, all right, let me write down what I've got here. Just wondering if I got confused when I was doing this afternoon. Or maybe I'm just writing it in So let's see, we've got...
Should the VI actually be VI of Y? Your last one? Oh, wait, no, okay, you got it, okay. Yeah.
I think actually there is a sort of mistake, but the thing came out right, so I assume that it's more or less okay. So let me see, this is 1, VI with pi 0. But the other one that we've got to have here is VI with this, but that's right here. And then we have V0 of Y with this one and that one. Okay, so this is, all right, I think I wrote it in a funny way, but this is basically right. Now, what things are non-zero? This thing is 0, but this one is non-zero. So in other words, the V0, pi 0 we computed, and that's something, delta of x minus z. So what I got was this, I m to the minus 2 minus 1 integral d cubed z, and then for this one, minus delta of y minus z. And then for this one, we can ignore these two terms which vanish, but this one with that one is the thing I computed over here, namely minus di of delta of x minus z. So this is minus di delta x minus z. And altogether, we get minus I n to the minus 2 di delta x minus y. Okay, so that's the Dirac bracket of di with b0. It's a derivative of a delta function. I can tell you what the other Dirac brackets are.
Are these derivatives of delta functions eventually going to work so as to...
The derivatives of delta,
Are these derivatives of delta functions going to end up working together in order to give us this like transverse delta function that we should expect to get with some theory?
I think you're right.
For the commutator?
Let me give you the rest of these terms. What I'm puzzled about here is why he doesn't have any D's under them. Oh, he was just going immediately to equal time commutators. And in fact, that's where the I came from. Somebody should have asked about that. The extra I here is because this is a, Weinberg was thinking of this as being a, he was implementing Dirac's procedure, which is, see, this is the definition of the Dirac bracket, but somewhere here I hope I wrote, yeah, what Dirac's procedure was to say the commutator of two quantum variables is I h bar times the Dirac bracket of the classical versions. And so an extra I crept into that equation because I was following Weinberg and forgot that Weinberg had slipped in. Weinberg was computing commutators rather than Dirac brackets. If we just stay with Dirac brackets, then we don't have the I, and in particular, di of x pi j of y, if we just call it Dirac, then this is delta ij, delta cubed x minus y, and all the others are 0. V0 of x pi j of y Dirac is pi mu x pi nu y Dirac. Those are all 0. Okay, and then, as I said, the commutator is then I times the Dirac bracket. So let's see if well, we're almost out of time. I was just thinking to see whether I can. Well, if you now just multiply all the Dirac brackets by I, you get the commutators, and these commutation relations turn out to be the ones, if you just assumed reasonable you just assume that the VIs of x with pi j of y was I delta ij delta cube of x minus y. So these would be the canonical commutation relations with vi of x, of course, the j of y is 0, and pi I of x, pi j of y just equal to 0. So in other words, you just these are, in other words, Dirac's procedure in this case gives you what you would expect. So I guess on Monday I'll try to relate this to the more interesting case of QED. And this is also one way of quantizing non-abelian gauge theories. All right, I guess we can stop.